All right, here we go again. Section 6.2, page 411. We're going to integrate by substitution, but this time we're going to throw e into it. So a couple things I want to remind you of. The derivative, d dx, of e to the x was e to the x, so the integration of e to the x is going to be e to the x plus c. We do have to be careful, though, as we do this, because e has to have a single variable in order to be able to integrate back and forth fairly easily. So with integration by substitution, if we have a single e, we're normally going to see that u substitution be the exponent of e. If there's more than one e, there's a couple things that can happen. It can either be adding or subtracting a couple of e's from each other, in which case we're going to split up that integration into a couple different integrations and then integrate separately. And if it's a multiplication or division problem, our u is normally going to be e to one of the powers. And if it's in a quantity with multiplication, it's normally going to be that quantity, or that part that's in the quantity, being our u. And if it's a division problem, it's normally going to be the denominator, or part of the denominator, as being our u for our u substitution. So let's go ahead and work through a couple of examples here. Got quite a few of them for you today. So sit back, relax, and let's enjoy it. So example 1, we have the integration of 4e to the 4x dx. Again, e does not have a single exponent, or a single variable exponent. So we're going to do our u substitution in order to make that exponent a single variable. So if we let u equal 4x, then du is going to equal 4 dx's. Well, I have a 4 dx in my integration, in my integral, or my integrand, and I'm going to replace my 4x with my u. So I have my integration then of e to the u du, which now becomes a very nice, easy integration problem. The integration of e to the u is e to the u plus c. We're going to replace that u with our 4x. So we have e to the 4x plus c. And that's going to be our integrated form, thus ending the problem. We're going to get a little more complicated in example 2. Example 2, notice we're going to let our u, again, equal that exponent of 2x. du now is going to equal 2 dx. And as I look at my integrand that I have 3 dx's. So I really can't use the 2 dx. So I'm going to divide that 2 over, and I get a half du equals dx. Now I'm going to take this 1/2 du, replace my dx with that. My 3 is staying this time. So I have the integration of 3 times my 1/2 gives me 2. Remember, 3 times 1/2, multiply across, we get 3 over 2. E, my 2x, my exponent, is now my u du. This 3 halves is a constant being multiplied to e to the u, so we could really think of it as being outside of that integration symbol. Doesn't really matter if you do or not. But we know the integration then of e to the u is e to the u. So I have 3 halves e to the u plus c. Replace your u, again, with our 2x, because that's what u was. So we get 3 over 2 e to 2x plus c. We could write this as 3e to the 2x all over 2 plus c. Continue on to example 3. Here we have 2x to the third, and we're multiplying that to e to the x to the fourth minus 1. Again, it's all being multiplied together. There's only a single e, so I'm going to let that exponent be my u. Taking the derivative, du is going to equal 4x to the third dx. Now if I look at my integrand, I have 2x to the third dx that I want to get rid of, or part of at least to get rid of. And if I look over here, I have 4x to the third dx. If I divide this side by 2, then I get 1/2 du equals 2x to the third dx, which is exactly what I want over here for my substitution. So I have the integration of 1/2 e to the u du. Again, the integration of e to the u is e to the u, so I end up with 1/2 e to the u plus c. Replace my u again with x to the fourth minus 1, so I have 1/2 x to the fourth, 1/2 e to the x to the fourth minus 1 plus c. Again, these are all equal to my original function, f of x. And that's our complete integration. In example 4, we're going to get a little more complicated. Notice here we have e to the 4x over e to the 4x, then minus 2 dx. So we could do a lot of different things with u, and u, remember, can be whatever we want it to be. So if we were to let u equal just that exponent of 4x, then I would have du equal to 4 dx, which is not a problem. We could divide that 4 over, and we have a 1/4 du equals dx. So if I were to do that integration, and I'm going to come off to the side since we know this is going to give us some issues, I have 1/4 times e to the u over e to the u minus 2 du. Again, I replace my dx with the 1/4 du. My e to the u, my u was 4x, so I have e to the u over e to the u minus 2. We can't integrate, again, when we have that u in the bottom. I could bring it to the top, but that's going to make it to the negative exponent, and it's just really going to be very cumbersome in order to get this to work out. So to make our life a little easier, again, if we have two things being multiplied together or divided, I'm going to cross this out, generally going to my u equal the denominator, or at least part of the denominator. So if u equals e to the 4x minus 2, now if I find the derivative, I have du equals, remember the derivative of e to the 4x, I take the derivative of the exponent, then my exponent does not change, derivative of minus 2 is 0. And then I have my dx. So now I have an e to the 4x dx in the substitution, and I have it in my integrand up here. All I got to do is get rid of that 4 now. So I have 1/4 du equals e to the 4x dx. Coming back over to my integration, now I have 1/4 times 1 over e to the 4x minus 2 is going to be my u du. We're going to end up with that 1 up there because that e to the 4x dx is really equal to 1/4 du, or 1 e to the 4x dx. So I can leave that 1 up there. So now I'm integrating 1/4 times 1 over u du. Integration of 1 over u? Yes, the natural log of the absolute value of u plus c. I can replace my u with e to the 4x minus 2. And again, there's my original function, f of x, is equal to the natural log of the 1/4 natural log of the absolute value of e to the 4x minus 2 plus c. Example 5, we're going to see that we're adding 2 e to the x's. Here we have the integration of e to the x. We know the integration of e to the x, e to the x. We don't know the integration of 3e to the 2x. So what I can do is I can split this up into 2 different integrations being added together. So I'm going to take the integration of e to the x dx, this part of it, plus the integration of 3e to the 2x dx. Now if I integrate e to the 2x, I can do that. Integration of 3e to the 2x, I would use my u substitution. So u is going to equal 2x. du equals 2 dx's. Can't use that 2, so I'm going to bring it over. So we have a 1/2 du equals a dx. So now my problem becomes the integration of e to the x dx plus the integration of 3/2 e to the u du. I can go ahead and integrate each of these now because they're e to a single variable. Integration of e to the x gives me e to the x plus c, plus the integration of 3 halves e to the u is 3 halves e to the u plus c. Replace my u, and we can talk about these c's. If I have a c plus c, well, this is a constant plus a constant. And a constant plus a constant is simply going to be a constant at the end. So we don't need to write it as 2c because 2 times a constant is still a constant. So this kind of goes along with our discussion of c and how fluid it's going to become. C is going to take on a lot of different values, and it's going to change within our problem quite a few times. So we have e to the x plus 3 halves e, our u now is 2x. And let's talk about that, that value here, this function. Because I noticed on a lot of our homeworks last week, when you were turning them in, you went ahead and found a common denominator, which is great. We want to do that. And we end up with 2 e to the x plus 3 e to the 2x over 2 plus c. And this is normally the way we're going to write this. We're going to leave that plus c kind of out on the end by itself because it's just a constant. Now, is it wrong to put it in as a common denominator or give it a common denominator? And it's not. We would have 2 e to the x plus 3 e to the 2x plus 2x, or 2c, sorry, over 2. But what is 2 times a constant? It's simply going to be another constant. So notice how fluid that c becomes. So normally the way you're going to see it written is over here. And this is more the accepted way of writing that plus c, just leaving it at the end. No need to put it as a common denominator. And that might make a little less confusion for you as you go forward. On number 6, here we have a couple things happening. We have addition of multiple e's here, and this first part of the integral, we have a quotient. So again, I'm going to split up this addition to two different integrations. So I have e to the 2x over 2 plus e to the 2x dx, plus the integration of 5e to the 3x dx. Now I can go ahead, remembering if I have a quotient, I'm going to let my u be that denominator, 2 plus e to the 2x. So my du is going to be 2 e to the 2x dx. I can't use the 2 in the numerator there, so I have a 1/2 du equals e to the 2x dx. So my integration is going to become 1/2 times 1 over u du. Over here, I let my u equal 3x. Well, I've already used u over here, so generally if we already used u, we go to another variable, call it what you want. I'll use v. So v now is going to equal 3x. dv then is going to equal 3 dx. Can't use the 3 because I have a 5 there. So dividing it over, I have a 1/3 dv equals dx. So this becomes the integration of 1/3 times 5, so 5/3 e to the v dv. Integration of 1/2 times 1 over u. 1 over u is our natural log. So I have 1/2 the natural log of the absolute value of u plus my 5/3 integration of e to the v is e to the v. And again, I'm going to put that plus c at the end. Replacing my u's with 2 plus e to the 2x and v with 3x. I end up with a final answer of 1/2 the natural log of the absolute value of 2 plus e to the 2x. To that, I'm going to add 5/3 e to the 3x plus c. And that gives me my final answer. Again, we could come up with a common denominator, Common denominator for these two terms would be 6. So our final answer, if you want common denominator, would be 3 natural logs of 2 plus e to the 2x plus 10 e to the 3x all over 6 plus c. And that would be a nice, clean answer with a common denominator. Give you example 7 just because it's a little more fun and it's a little more exciting. Here we have a quotient, but we don't have multiple e's. We still have just a single e here. So u is going to be, again, just that single exponent of what e was. So it's e to the square root of x, so my u is going to be the square root of x. If I had multiple e's, then I'd go back and see if I'm adding, subtracting, multiplying, or dividing to see how I attack the problem. So here du then is going to be 1/2. Remember, x to the, or the square root of x is x to the 1/2. So the derivative is 1/2 x to the negative 1/2 dx. If I think about x to the negative 1/2, that is 1 over 2 x to the 1/2 dx, or the square root of x. I have the square root of x in my integral. So all I gotta do is get rid of that 2 by multiplying it over to my du. So 2 du's is going to equal 1 over x to the 1/2 dx. Going back to my integration, I have a 2 there. I'm bringing another 2 in. So I have 4 integrations of e to the u du. Integration of e to the u, again, is e to the u. So my original function, f of x, is going to equal 4 e to the u. U, again, was the square root of x plus c. And that's going to end our examples for the integration of e to a function that's not a single variable.